This is going to be the first lecture over sections 1 through 3 in chapter 23. We're going to be looking at electromagnetic waves, speed of light, electromagnetic spectrum, that kind of thing. So in the summary here, what we're seeing is that when either an electric or a magnetic field changes with time, that a field of another kind is induced in the adjacent regions of space. This electromagnetic disturbance or electromagnetic wave can travel through space even when there is no matter in the intervening region. In other words, if there's just empty space, you will still see this particular wave. So in a vacuum, electromagnetic waves will travel at the speed of light, which is rounded to 3 × 10⁸ meters per second. So the electromagnetic spectrum is going to cover a range of frequencies from at least 1 Hertz to 10 to the 24th power of Hertz, and a corresponding broad range of wavelengths. Radio waves have low frequencies and gamma rays have high frequencies. Visible light is a very small part of the spectrum with wavelengths in vacuum from 400 to 700 nanometers. So let's take a look at these sections. So again, you may remember from Faraday's law telling us that a time varying magnetic field, in other words, a magnetic field that changes over time, acts as a source of an electric field, as shown by induced EMF in inductances and transformers. So in 1865, a mathematician and physician, James C. Maxwell, proposed that a time-varying electric field could play the same role as a current as an additional source of a magnetic field. In other words, you vary a magnetic field, you get an electric field, you vary an electric field, you get a magnetic field. That's what he's driving at. This ends up this relationship that you have there ends up with a set of 4 equations called Maxwell's equations. They are complex, but they tell you a lot about what you see regarding changing electric and magnetic fields. And there's some pretty amazing results there out of that, actually. If you're a big fan of the radio, in order to produce the signal, a radio station sends an appropriately modulated alternating current into the antenna of its radio mast, and the time-varying current creates changing electric and magnetic fields. An electromagnetic wave is then emitted. When these fields reach your antenna on the car or whatever you're listening with, the process is reversed. The changing fields create an EMF in the antenna, and the radio selects and amplifies a narrow band of frequencies emitted by a particular station. So when either an electric or magnetic field is changing with time, the field of the other kind is induced in adjacent regions of space. So the time-varying electric and magnetic fields can propagate through space from one region to the other, even when there is no matter in the intervening region. And this is referred to as the electromagnetic wave. So one outcome was his prediction that an electromagnetic disturbance should propagate in free space with a speed equal to that of light, and that light waves, therefore, very likely to be electromagnetic in nature. So in 1887, Heinrich Hertz used oscillating LC circuits, which we've discussed in a couple of chapters back. Using those, he produced in his laboratory electromagnetic waves with wavelengths of the order of a few meters. Hertz also produced electromagnetic standing waves and measured the distance between adjacent nodes to determine their wavelength. Knowing the resonant frequency of his circuits, he then determined the speed of the waves from the wavelength frequency relationship, and so Hertz confirmed that the wave speed was the same as that of light, and that verified Maxwell's theoretical prediction directly. That's a pretty outstanding method to make that determination. So the SI unit of frequency, or 1 cycle per second, is named in Hertz in honor of Heinrich Hertz. So the synthesis, wrapping up the basic principles of electromagnetism neatly and elegantly in 4 equations, is one of the biggest achievements that we have actually made up to this point. It is comparable to Newton's contributions to mechanics and to relativity, quantum mechanics, DNA. It actually is, without exaggeration, something that is highly important in our understanding of how you can deal with the matter and waves. So let's go on to chapter 2 here, the speed of the electromagnetic wave. So if we take a look here, using a rectangular coordinate system, we're going to imagine that space is divided into 2 regions by a plane perpendicular to this x-axis. So you got this plane going right here. At every point to the left of this plane, there exists a uniform electric field. So in other words, you get an electric field that's sort of bouncing up, potentially up this way, down this way, up this way, down this way, that kind of thing. And then you've got a uniform magnetic field in the z direction, which is out this way. So while you've got E moving up and down this way, you've got B that's moving in a plane this way. I want to see if I can find a dynamic graph here that will kind of show you what all of that is about. But back to this particular example, we're going to suppose that the boundary plane, or the wave front, moves to the right with a constant speed. We don't know what it is, but E and B travel, those fields travel to the right into previously field-free regions. In other words, they're going where they haven't been, with a definite speed. And so this is described as a rudimentary electromagnetic wave. So the electromagnetic fields are uniform behind the advancing wavefront and 0 in front of it. So we're not going to concern ourselves with the problem of producing this. Instead, we're going to ask whether it is consistent with the laws of electromagnetism. So when an electromagnetic wave travels in a vacuum, the magnitudes of E and B are in a definite constant ratio. The wave front moves with a speed c, which is given by this, where E naught, epsilon naught, and mu naught are proportionality constants, which we encountered with Coulomb's law, and the magnetic field of a long straight wire, respectively. So when we insert those into this particular equation, this is what we come up with. And that is, in fact, the speed of light. This is an interesting little application here. So nuclear reactors and their radioactive fuel rods are often submerged in pools of water that absorb the radiation. And these pools glow with the gorgeous cerulean blue light you see in the photo. And this glow and is an example of a phenomenon called Serenkov radiation. And it's caused by energetic electrons that travel faster than the speed of light in water. Nothing can travel faster than the speed of light in a vacuum, but there's no law against exceeding the speed of light in a given medium. So the fast electrons, which originate in nuclear reactions, and that's a whole nother chapter, interact with atoms in water, which emit light. And because of the electron speed, these interactions are confined to a shock wave like that of a supersonic jet, and the emitted light is mainly blue. So our assumed wave is going to be consistent back to this situation right here. With the principles of electromagnetism, provided the wavefront moves with the speed just given. We recognize this as the speed of light in a vacuum. And the epsilon naught appears in the equation that relates an electric field to its sources, and mu naught plays a similar role for magnetic fields. So this is for electric fields, this is for magnetic. Since the electromagnetic waves depend on the interaction between these two fields, we might expect that those constants would in fact play a role, which they do. So we've chosen a simple and primitive wave for the study in order to avoid mathematical complications, but the special case illustrates several important features of all electromagnetic waves. So the characteristic of electromagnetic waves in a vacuum: the wave is transverse, so both E and B are perpendicular to the direction of the propagation to the wave and to each other. And let me see if I can find an example here to kind of show you that. Okay, so here I've got a graphic here that's going to kind of show what's going on. So you can see here, as the electric field is in blue, and as that comes about, that the magnetic field is in red. You will notice that as the amplitude of the electric field increases, you see the amplitude of the corresponding magnetic field increasing. And these are at right angles with each other. So as they move, as they propagate, you can kind of see how this moves forward. As it moves up and down or whatnot, you will see the corresponding magnetic field also change shape. And so that is what we're looking at up here, except it's in motion. So the wave, again, is transverse. There's a definite ratio between the magnetic fields. In other words, there's going to be some sort of proportional effect. As one increases, the other will increase, and that's what the value of C is supposed to be. The wave travels in a vacuum with a definite and unchanging speed, C. And unlike mechanical waves, which need the oscillating particles of the medium, such as water or air, to be transmitted, the electromagnetic waves do not require a medium. And that's sort of unusual when it comes to waves, but that's what we have. That's what we understand. So looking at the right-hand rule, if we hold your hand flat, then this is going to be your right hand, with your thumb out at a right angle. If you point the thumb of your right hand in the direction the wave is traveling, in other words, this direction, just like what we saw in the graph up there. So the wave is traveling in this direction with your fingers pointed in the direction of the electric field. If you hold your hand in place and bend your fingers through 90 degrees, you will see your fingers will point in the direction of B. You can also think of it as the way that your palm is facing. In other words, your thumb is pointing in this direction, in the direction of the propagation of the wave. Your fingers are pointing in the direction of the electric field. Your palm would be pointing in the direction of the magnetic field. That's the way I would look at it. Okay, so you have some other problems here that you can work through in this particular section. Now, let's go on to the electromagnetic spectrum. So with the electromagnetic spectrum, there is a wide range here. Even though everything is moving at the same speed, that doesn't necessarily mean that everything is the same wavelength or the same frequency. Far from it. What you were looking at here is quite the range for different types of waves. You can see down here that the wavelengths here, as you move from here all the way down to here, that the wavelengths start to get much, much shorter. You can see the frequencies are going to be moving in the opposite direction. As you go from here to here, the frequencies start to vastly increase. So as the wavelengths start to get shorter, the frequencies start to get much, much faster. Down here for the longer wavelengths, you have radio and TV, and then you move up to microwave, then infrared. Right here in this small band, you're seeing visible light. That's very important to us because that's how we perceive the world. Then you go to ultraviolet, then you go to X-rays, and then gamma rays. And you can see the frequencies here as we increase, or as we decrease the wavelength. In other words, the wavelengths get shorter and shorter and shorter. The frequencies here, how many cycles per second can pass a certain point, start to get much, much quicker, or start to have, it can happen far faster than what it was before. So again, here's another application that the green color of plants is obviously directly related to photosynthesis. Plants are green because green is the color of light that plants don't use during photosynthesis. As you can see from the graph, the plant chlorophyll molecules absorb violet, blue, yellow, orange, and red light. All of this light contributes to building sugar molecules, everything but green. The green light that is not absorbed is reflected and transmitted, so plants appear green. Why don't the plants use the green light? Although scientists don't quite know the answer for that, one possibility is that the ancestors of today's plants evolved chlorophyll-based photosynthesis at a time when the planet's dominant photosynthesis organisms used the molecule retinol, which absorbs green light and reflects the red and violet light. And those red and violet light appears purple. And for this reason, the hypothesis is sometimes called the purple planet hypothesis. The ancestors of today's plants may have to make use of what light they can still get, resulting in the chlorophyll spectrum. Although photosynthesis purple bacteria still exist, chlorophyll-based photosynthesis came to dominate over time. So by using special sources and filters, we can select a narrow band of wavelengths with a range of, say, 500 to 501 nanometers. That is considered to be monochromatic. Absolutely monochromatic light with only a single wavelength is an unattainable idealization. When we use that expression with reference to laboratory experiment, we really mean a small band of wavelength around 500 nanometers. One distinguishing characteristic of light from a laser is that it is much more nearly monochromatic than light produced in any other way. Science and technology use all parts of the electromagnetic spectrum. You can see how wavelengths and the radio, infrared, visible, and X-ray parts of the spectrum are used to explore the galaxy Andromeda. And you can see all of those different ways of viewing that particular galaxy. I mean, we can see this if we were actually, at a distance where we could see it other than just a dot. But if you look using different wavelengths, these are the impressions you got. So it's all a matter of perspective.